Great. Thank you so much. I hope you can see the slides okay and hear me okay.
That's perfect. Thank you.
Wonderful. Well, thank you so much for the invitation. And also, thank you to Tony to getting us started with such an interesting tool. So we're moving from flavors and fragrance over to pharma. And today I'm sort of here more as my ACS Green Chemistry Institute Pharma Roundtable co-chair hat, and really looking forward to sharing with you some of the things going on. In the interest of time, I'm kind of going to give a broader overview and go into detail of one tool in particular, which is actually the process gas intensity tool, which relates to Robert's question. So let's get started. The roundtable is a global industrial collaboration dedicated to catalyzing the integration of green chemistry and engineering in the pharmaceutical industry. So at the moment, we have over 40 member companies really spread throughout the world. This is just a snapshot of our current membership. And we were formed back in 2005 with the goal of really integrating green chemistry throughout the life cycle of a drug. That's research through to development and then large scale manufacturing. So initially, the roundtable was really focused on manufacturing, and the key participants were really process chemists. But this has really expanded as we acknowledge, it's really important to integrate green chemistry as early as possible into the development life cycle of a drug. Really implementing this in early discovery and phase one activities can really deliver large paybacks later. So the roundtable, of course, we're all competitive companies, but we acknowledge that we really share similar challenges and toolbox for solutions. So those include innovative chemistry, a really talented scientist, the supply chain, green technology. And so this gives us a way to collaborate and invest in shared items to bring the industry forward in terms of green chemistry. So we formed around these four strategic pillars, and one particularly relevant today, of course, educating leaders, and also tools and metrics for innovation. We also have a significant grants program. That's where the largest component of our membership fees go to, and so I encourage you to check out the website for grant funding opportunities as well to share within your academic institutions. In terms of today, I'm sure the team was aware of the Chem 21, a previous green resource. This has been offline for quite a while as hosting items have shifted. And so the roundtable has really acknowledged the importance and really vast amount of information that this website used to provide. And so we're really pleased to share that this has been relaunched and is going to be hosted by the roundtable. We actually have a sub-team within the member companies where we're looking to continually update and add to the content here. So I encourage you to check this out. This is available through our website. We also do a lot of work in terms of sharing the industry perspective. So I just wanted to highlight this briefly today as an opportunity of pointing your students towards things that actually show what pharma is doing. And if they're interested in moving into industry, this can give them an insight of what kind of chemistry we're interested in, what are the things that are going on, and what are the challenges to maybe support some grant proposals or something. So one of this are these green chemistry articles of interest to the roundtable. This is published in OPRD, and it comes out twice a year. The last edition, up to number 30 now, this has been a long-running activity through the roundtable, was published in September. And it just really highlights really interesting and innovative chemistry, which advances the field. So it might not be something that's green in all sense of the word, but it represents an improvement from the perspective of the authors that come from pharma companies. Another one is, the roundtable sub-teams have put out a lot of perspective papers that look at current challenges in therapeutic areas. So I've just highlighted a few recent publications. This focuses on oligonucleotide manufacturing, peptide challenges, and also biologics. So the goal of these papers are kind of to highlight the challenges and encourage collaboration. And then finally, the Roundtable has published these benchmarking activities. And I've just shown the breakdown here for the process mass intensity. I'll go through the metric later. But this sort of shows in the different therapeutic classes of different types of drugs, what are the big contributors to the mass and resource efficiency. So for small molecules, you can see the breakdown in solvent, oligonucleotides, highest contributor is water. And so I think this provides kind of an interesting overview of what are the resources that are going into making these different types of drugs. The peptide manuscript, it's going through company approvals, so it'll be submitted shortly. So please look out for that one in JOC. Okay, we also developed tools and metrics, which will be the focus for the rest of today. These are all hosted on our website. And they might come from activities within the Roundtable or maybe member companies that have developed a tool and have shared it to be shared publicly to support green chemistry integration around the world. So one of them is a solvent selection tool. It's an interactive tool that has up to 272 solvents. It includes physical properties, functional groups, health and safety elements. And you can start looking for solvent alternatives in this tool. Dots that are close together are likely to have similar properties to those that are right around them. The reagent guides are a fantastic resource. They have a whole different set of transformations. I've just shown some snapshots for fluorination. And industrial chemists have placed these in terms of utility, scalability, and greenness. So we want to sit in the middle, but it takes a look at the reagents. It provides mechanism, background, scale up examples. And so, if your students are looking for a new reagent, this is a great way to find something that the industry would feel appropriate for use and scale. The biocatalysis group put together this cheat sheet of commonly used biocatalytic transformations. And so this gives an idea and some red, light, and green flags for things that have wide utility and broad scope. So again, all of these are available on the website. In terms of metrics, we have some tools there as well. Process mass intensity, I'll go through this as a demo, as well as the analytical greenness calculator. This lets you take a look at how green your methods are for the analysis of your compounds, checking for purity, etc. And then this is a really awesome app where it came from us from BMS. And it basically lets you look at different routes to the same compound and determine based on industry benchmarking and industry data, what is likely to be the most efficient route. So this is kind of an AI approach where you can screen different routes to see what has the highest potential to be efficient, kind of before you even run an experiment. So metrics really important and something that we use every day. Green metrics in particular, and process mass intensity has really been the key metric for the pharmaceutical industry. The goal is really to use this metric to drive development. So looking for places of inefficiency and figuring out where we want to invest and make improvements. So we like this because it's very straightforward. You can even calculate it from your electronic notebook with just the press of a button. And so I think this is a metric that students looking to move into industry should be aware of. And if they have calculated it and kind of use it in their studies or in the laboratory, that would be very impactful. We calculate it for all of our chemistry steps, and we track it through development, where you expect it to decrease as you improve the process. So just shown some examples here. PMI in plant manufacturing. So this is kind of a schematic of a plant operation. We have our reactor, we charge our substrates coming from drums or fiber drums. We might do a reaction check, a quench, maybe a layer cut. We crystallize and filter, we dry, and then we pack in drums. And so we can start just taking the mass of the inputs divided by the mass of the product that you isolate, and you get a PMI. You can translate this, of course, to the laboratory, where we might be working on smaller scale. But again, it's still substrates and reagents kind of going into the reactor, maybe an aqueous workup, filtration and drying. And again, I just scaled this, so you might get a PMI of 40. So I think this is something that students could do based on any of their lab experiments. And then finally, when we're kind of communicating to the broader community, we really like to make the example to the kitchen. And so I've just included here a PMI from a loaf of bread, where you're bringing in all the ingredients. You just divide by the weight of the bread that you isolate at the end. And I guessed at these numbers, but this is a very efficient PMI. We would be thrilled to have a chemical reaction with a PMI of 2. So just an idea in terms of communicating with different levels of students, and perhaps a way to bring it into education. So I want to just flip now and show you the tool that you can use for PMI calculations. Here is our website, the ACS Roundtable website. I hope you can still see my screen. Can I just get a thumbs up, perhaps?
Yes, we can, people.
Okay, great. So we just go to Tools for Innovation. Here are the 4 strategic pillars. So there's a lot of other resources that you can look at. So we just scroll down to reagent guides, the solvent selection guides, that's the interaction one that I shared. And we have this convergent process mass intensity calculator. So you can just download it and it'll open an Excel. So the Excel file I've brought up here, there's kind of an introduction instructions tab. There's a summary table tab that shows you all of your steps. This is sort of built for industry, and so that's why there's so many steps included. So you can actually do up to 11 linear steps, and then you can bring in multiple fragments to do kind of convergent chemistry to cover your whole supply chain. So that might not be necessary for the lab, but this tool gives you a really broad ability to capture a lot of steps. So this is sort of what the first tab looks like. And what I'm just going to do is do the calculation from our example. We can do the bread, or we can do the plant. And so if we come down here, this is the step 1. The first thing you would do is put in the batch size. So that would be of your limiting reagent. So that'll come from your substrates and your reagents. So I'll just say my substrate 1 is 50 kilos. We'll do substrate 2 as 20, and we'll do a reagent as 30. So that gets us to the kind of that first 100. We can put in our solvent, say ethyl acetate. We can put in our water for the quench or workup. That'll be 200. Organic solvent will be 500. And we can put in our batch size. So this will be the limiting reagent. So that would our 50. And then our output is going to be 20. And so overall, you can see our PMI is 40, which is great. There's always a risk when you do a live demo that you type something incorrectly and it doesn't match the slide. But you can see here our set PMI is 40. And so this would be very straightforward, I think, to follow along for any experiment that a student has run. They can just enter it in here. I've also pre-loaded another example that I'll just go to now, and that's just Lipitor. So I just Googled, top US prescription drugs. and downloaded a patent. And in the patent, it has the weights of the things that are charged. And so I just took a little section of the synthesis of Lipitor here, the final deprotection step, and then the salt formation. And I just took those and entered from the experimental in the patent all of the information. So you can see here, they do kind of a crude isolation, then a purification, and then a form change. But all I've done is gone through and added in those values in the different sections. So this is to make the purified compound, then the crystalline compound, and then the final isolated calcium amorphous. And so this is just a snapshot of the experimental. I just took the numbers from here and plugged it in. And you can see that we get a step PMI that gives us all of the mass intensity, so reagents divided by product for this step, and then it gives you a cumulative PMI over the 4 steps that I've entered. So this is really interesting. You can see how making changes or improvements impacts the PMI. So here we have 187 kgs of input raw material are needed to make 1 kg of the final product. So if I come in and I say, oh, we can do some process chemistry improvements and increase the yield of that first step, let's say instead of isolating 8 kilos, that allows us to isolate 9 kilos, that gives you you can then look at the change in the PMI over the full item. So you can see the impact of increasing yield. You could also see the impact of like decreasing some solvent. So this has a pretty high methanol charge here. So what if through process improvements, we were able to decrease the need for that solvent to 100 kilos instead? Again, you can see the impact of that on a step or a PMI. You can also look at these and say, okay, which of these steps is the most inefficient? That would be step 1. We need 66 kilos of raw material to make 1 kilo of the intermediate. And so this might be where I choose to invest for my process development. So I hope this gives you some ideas. We can put this into context in terms of just the estimated number of patients that are on this drug. This is from 2022 and the website linked here. So if we have sort of 26 million people taking this drug daily, we have 40 mg of that final product in each dose. That gives us actually an amount of how much we're making per year. So at least 389 metric tons of this material is made every year. When you think of a PMI of 187, that means over these last 4 steps, we're generating, a huge amount of waste just to supply these patients in the US. We can then kind of put it into context of waste per patient per year, et cetera. So I think there's hopefully a lot of opportunities within this simple metric to sort of show the impact that green chemistry can have, put it into context in terms of supply and patient demand, and how integrating these concepts early on and how we think about green chemistry can really have an impact on your patient, on your students, and put that into perspective. So that's what I wanted to share today. Please reach out if you have any questions, and I'll stick around for the breakout session